Esto cambia la regla, siempre es bien fino, todo el mundo lo que sabe lo que está diciendo, tiene que estudiar. Sí. O sea, no es que puede pasar, mira lo que estoy esperando.
Welcome everybody. It's a pleasure to introduce you Professor Dante Chialvo. Dante received his degree in 1982 from the Universidad Nacional de Rosario in Argentina. I think that a degree in medicine. And then after this he had a position at the Department of Physiology of the University of Rosario. Then he moved to several places in the USA. He was associate professor at the State University of New York, at both at the Department of Pharmacology and the Neuroscience program. Also, he was at the Santa Fe Institute for the Science of Complexity. And he was also a professor at Northwestern University in Chicago. And now he is associated to the University of California, Los Angeles, and also has a position from CONICET at Rosario. He has written above 100 of papers, and all of them devoted to the understanding of natural phenomena from the point of view of nonlinear dynamics and complex systems. Today there is in the El Mundo newspaper, there is an interview to him. He says he's fan of being working in dynamic lab. So this is the subject he studies. Has worked in a lot of topics related to natural phenomena, including the modeling, mathematical modeling of cardiac arrhythmias, molecular models, neural coding, self-organization and collective phenomena in ant swarms. Also, he has some recent surprising paper on paleoclimatology. But most of his recent work is devoted to the understanding of brain, emerging phenomena in the brain. In fact, he's now visiting the psychology group led by Pedro Montoya in Mallorca. And the topic of his talk today is criticality, brain physics, and mind dynamics.
Very good. Thank you so much again. I guess that it's common to say that it's a great pleasure to be here. Thank you to the organizers. And I guess that I am not anymore the oldest, most frequent visitor of the university because Professor Plastino did me for a couple of years. But I can beat Professor Plastino by one thing. I think that I hold the two most cited paper of Imedea, together with Victor Reviews. The other day I discovered that the two most cited papers in Imedea and the history of Imedea are one of the papers that I will be talking today with Victor Reviews. And the second most cited is a paper in Nature by Vidasso. And so it is a great pleasure. I guess that I need to write a couple more papers with some of you guys. And actually, those papers that I mentioned have something to do with collective processes. And it's not my merit, but it's the fact that the topic of collective processes for the last 20 years have exploded in all areas. And it so happened that I was there when this thing started. And in the article of the newspaper today, they clipped the last part of the interview in which the journalist was asking me which project I was working recently. And I said that I was working on a book for children. It's titled is ¿Qué tienes en la cabeza, niño? And that book is about questions that people ask me And these questions were originally questions that physicists 20 years ago were asking, why within the brain? They were questions without preconceptions, usually fundamental questions, which are also the questions that children ask you. Children ask you, why I need to learn? Why is it useful to go to school? So the book that I'm working on was motivated by this similarity of the question that I was being asked maybe 15 years ago when I started visiting in the day. And I don't know if I answered some of those questions. I still have many more similar questions. And today I will be sharing with you this kind of questions. So this is just a show off. You can read the abstract. But basically, I don't know how it works. Which button?
It's not in faster. It's not going more. So you need to push, you need to put the keyboard. Use the keyboard.
That's a laser pointer, the red.
Which one is the laser?
Red. Yeah.
When it works, it's battery relays.
Okay.
Use your finger. There you go.
It was not red.
Okay. Okay, so let's get organized. This is the work I'm going to be talking about. Basically have 4 groups, one in Buenos Aires in the physics department. This Ariel is a student right now, Sergio Montero is another student. Enzo Tagliasucci now moved to Frankfurt doing a postdoc. And Pablo Valenzuela, probably you know also from the physics department, Daniel Freiman from math. The collaborators are also engaged in the fMRI work, Dr. Montoya from the psychology department and Miguel Munoz here in the audience. And these are the people that are getting the data from fMRI in UCLA at Los Angeles. And basically, everything that I will be talking today is about data and theory. And I want to be serious about this because none of the claims that I'm going to make is an empty claim. So you can challenge me to say where you have the evidence that this have anything to do with reality, and I will be able to show it to you. And I was thinking for this particular audience how to describe in a single statement what it's all about. And it's all about, you can look at these 2 books. One book is from my friend Olaf Sporn, Network of the Brain. The other book is from Gustavo Leco and Edmund Rhodes. Gustavo is in Barcelona. It's called The Noisy Brain. These are 2 books that I highly recommend. These are extremely good books. But both failed in a fundamental aspect. This book describes the brain as a network of components that are talking to each other. Now, if you take seriously the claim and you go through the 250 pages, you will ask the question, if the brain is a network, where is the router? Who is holding all these connections? And this is a fundamental flaw, which nobody wants to talk about. But this is one aspect that I will be talking to them. If the brain is a network, somebody has to be having another brain to make this brain work. And it's not a trivial question, and the answer, of course, is not trivial at all. Okay, so Gustavo on Edmund Rhodes says, don't worry about this question. You can put some noise, and the noise will be making the switching of these connections. But again, if you put noise into the brain, where is the noise in the brain? This noise is an external solution, it's an external fluctuation, and physicists in biology will appreciate that the big difference between equilibrium fluctuation, non-equilibrium fluctuation, noise is a driver, noise is an intrinsic fluctuation of the system. So basically, what differentiates the rest of my talk of these 2 very good books is that we say the brain is not a network, the brain is not needing noise to do all this switching. The brain has to be in a particular regime to solve all these problems at once. And the solution will be that the brain stay in the point of phase transition between order and disorder, the brain state. Basically, that's the message that you will have. And this started about this time, in 1990, I visited Pervac, This is Bruhaven, this is Kim Christensen, now at Imperial. Oleg died a few years ago, and this is me, I'm still alive, and Pervan also died, so I'm scanning this way. So. And the joke that Pervan used to do with me is that I will tell Per, for me the brain is critical, I would be like, my brain is critical, and Per will say, yes, for me too that. And so the conjecture that it's important to see the brain as a system near criticality have these few points that I will try to make during the talk. I will make the claim that the brain seems a relatively small dynamical system. Okay? Again, physicists used to calculate things asymptotically for very large infinite systems, so this will make you uncomfortable. Don't worry, I will say that the brain is composed by a few dozen interacting atoms. And I will show you evidence that that's like that. That the brain is not billions and billions of independent components of neurons. There are a few, let's say 10 to the 2 components that are making my brain works. I will also make the claim that perform a very small number of behaviors, usually a few dozens. In psychology, we say thousands of things that the brain can do. So you see your friend in the business and you start writing, laughing, eating, whatever. You get 100, 200 and start repeating. So the repertoire that make a brain look like it's driving your behavior is also, let's say, 10 to the 3. So now I came to claim that even relatively small, and again, this is quote unquote, dynamical system, if are near a second order phase transition between order and disorder, we know that it's spontaneous, not with a driving force, not with noise coming from outside, will generate the largest variety of robust and flexible behavior. These are terminology which can be put more rigorously as metastable state. And you know that at criticality the system can use all the possible configuration that the end degrees of freedom the system has. So we say, if you want to build something that has a large repertoire, which is able to switch with just a tiny perturbation, the best place to be is not in the ordered, rigid regime, not in the very disorderly jumping all over, but it's in the middle. Okay, so the claim
how is defined metastable?
I will define in a minute all this terminology. Again, anybody need definition of metastable in this audience?
Well, I was confused because you were talking about tiny protuberances, and for me metastable means that you need an activation energy. So I was wondering what do you mean here by metastability?
That you really need that in order to follow the talk? How many of you need that definition to follow the talk? He's a director, that doesn't matter.
So we agree that you are misusing the word metastable state.
You were listening to me that I said all these quote unquote relatively small physicists used to do asymptotic and so and so. So relax your definition such that you can.
I just asked what was your definition of metastability. And you asked me why I was asking that, and I told you because I thought you were using something straight for me. And if I am confused, I can follow.
But now you are confused.
No, I am now rather clear that you were misusing the word metastability, so you can go on.
This is the list on inviting doctors to talk to physicists. And you
are not considered by doctors as a doctor, so we can just go on.
Okay, everybody's enjoying the moment?
Yes.
May I continue?
Yes.
Very good. So, the claim we are making is that some of the most fundamental properties, okay? He does always this to me last 5 years ago, he did it with the motions.
Yeah,
But it was 5 years ago. I forgot.
but you keep coming, so.
Okay. What is the camera? So Maxi promised me, we practice this all the time. It's gonna give me half hour more to make all these interventions. So commercial will have to do it. Okay, so the claim we are making is that the most fundamental properties of the functioning brain, which we are going to define in a minute, are possible just because stay at the border of such instability. Okay, so it will not work any other way. So this is a claim. I will have them support that claim or not, and this is the rest of the talk. Now, the point number 5 that I will try to make is that how much of the most relevant brain dynamics is due to connectivity or is due to collectivity. And this is not an empty claim. It is very, very common in neuroscience to talk about connections and to think about the brain as something that if two areas are excited in sequence, it must be a connection between this area and that area. It's so entrenched into the notion that there are tests to detect a structural connectivity, as it's called, in which the conduction delays, meaning the time that usually an action potential, which is the activation of the neuron, take to go from A to B, if that conduction delay measured incrementally match what is known by the physics of propagation, they will say this is possible. Otherwise, it's not possible. Now, all my talk will be to show that indeed, if you concentrate in connectivity, nothing of the experimental result that I will show makes sense. And that you have to forget about connectivity and you have to start thinking about the dynamic of collective processes, which in this audience is nothing new. The point is how much of the collective process we understand as a collective process and how much of that is an ad hoc explanation. So the plan, I guess, that is to run through the motivation, which is already I already started. You know, in this audience, it's not new that most of the interesting microscopic phenomena is a product of an underlying collective phenomenon. So neuroscience, in that sense, is going to explore if the microscopic phenomena is behavior, me talking or me knowing or memorizing or whatever, what is the collective process behind? Again, the big difficulty for the last 50 years is that this collective phenomena has been trying to understand as a connectivity problem. And most of the fundamental problems are not solved because we insist into seeing that neuron 73 connect to neuron 44 and 44 and 43, etc., are not seen as a huge number of degree of freedom interacting and doing whatever they're doing. So, I think I'm going to skip this, it's a nice joke, but I will in order to save time. So let's review what is special about being critical. Again, at the risk of being asked for asymptotic definitions, I will remind to those that are not very familiar to some properties that are good for our discussion. I'm using the transition from order to disorder in a magnet again, but this is just a qualitative description. I don't think that the brain is doing this particular transition with this particular characteristic. But in one side, for low temperature, we have a subcritical state in which all the spins are in the same, line up in the same direction. On the high temperature, you have that all the spins are each one doing whatever they want, uncorrelated, and there is no particular scale except the scale imposed by the interaction, the local interactions. On this case, there is no particular scale, the whole thing is all line up. But if you approach the critical temperature, you have islands, big islands of ordered spins. Inside this island, they have little lagoons with little islands with this particular description of a scale-free landscape of regions which are ordered and regions that are in the opposite direction. So it's only at the critical state in which you have this long-range correlation, which you can travel from one end to the other end of the lattice through the same island, I would say. And if you enlarge the system, you will have that this long-range correlation enlarge with the system. So you can have a very small system that you can travel all the way up, and you can enlarge the system, and this is only happening at the critical state. There is no other situation in which you have the same divergence of correlations. Now, again, imagine that you built a brain that worked this way, or imagine that you built a brain that worked this way. Again, there is no repertoire of behavior here, you have only one. Here there is no repertoire of behavior. Behavior in this case will be that each group of spins is a group of neurons doing a particular thing. Okay? And in the middle, at the critical state, you have, and now for Maxi question, you have the largest number of configurations. Let's not call it the stable, the configuration, in which each configuration will be one state, okay, in which each spin is. So this is one possible. You can imagine another one that have a different shape, but with all the same statistical properties. When I say that only at the critical state, you have the largest abundance of dynamical state, I refer to that. And that is an advantage that the brain can use. So which is related to another question, that why do we need the brain at all? So if you look at the world around us, you look outside, and let's say that you suppose for Darwinian reasons that you're interested where the food is. The food is not like in this case, in which it's all over, and every corner you turn you have food to survive. It's not like that, in which the food was yesterday there and tomorrow is not anymore. It's more like that, in which most of the time you find the food where you find it yesterday, but the situation can change, but it's not completely uncorrelated. So the brain is an object that allows you to get food, get mates, to pass your genes, and to escape from your predators. That's basically the value of brain. That's why you need the brain. Now imagine that you have to survive in a world like this, or in a world like that. In this case, you don't need a brain. There is food and mate and everything always in the same place. In this case, you don't need a brain because it's not of use at all. So the brain has to survive in a world that is critical, and physicists can argue if the world around you is critical or not. There are people like me that are convinced about that. So the reason why we need a brain, as I repeat, if the world is so critical, everything will be simple and uniform, there is nothing to learn. If in a supercritical world, everything will be changing all the time, it will be impossible to learn. I think that you agree with that. The brain is only necessary to navigate in a complex critical world. So when I discuss why we need to talk about if the brain is critical or not, it's important to keep in mind this. Because even if I show you data showing correlation, etc., in the brain, you'll say, yeah, but it could be some other reason why the brain has all this correlation. You will not find a brain that has this feature if the landscape of opportunities of food or whatever is different from what I'm describing here. It is a point so not trivial that indeed physicists working in JPL many years ago, when the first probe was sent to Mars, or to Venus, I don't remember where. The discussion among the physicists and the engineer was what to put in the probe to prove there was life out there. And the instrument sent in the first probe, or instrument that Loveloy described as sending somebody to prove that there is life in the Sahara Desert with a fishing pole. Because the probe that was sent to measure stuff in Mars or Venus was only good to prove that there was life like us. Right? So like searching for fishes, but landing in the Sahara Desert. What Loveloy suggested was that you have to only measure the statistic of the fluctuations in some, either CO2 or temperature. And if the statistic were the type of statistic of non-equilibrium that we know of, then you can have a scheme if it was live or dead. So that's the reason why I insist in this part of the talk, which is the most fundamental reason why we should look for signature of criticality in an object that is supposed to be good to make you survive in a particular environment. So let's suppose that we are right and that the brain is critical because the world at large is critical. That will allow to have reconfigurations, meaning changes the functional connection between areas in the brain that will give some flexibility to adapt in that environment, which is all what we do to life. And that will only be possible if the brain operates near a second order, for instance. If we are right and the brain is critical, then came the experimental part. What one should be able to observe. This is a list without all this reference over here, which I made a few years ago, and I divided arbitrarily in things that you should see a large scale. A large scale, you should see this Einstein-like scale-free networks, which I'm going to show you later, which means these long-range cortical correlations, which are distinctive of this continent with lagoons, with islands, with this fractal distribution of domains. You should see this at first, and this is what we did with Victor Deleuze a few years ago. The second thing that you must see, is a divergence of correlation rates. Meaning, if you observe the correlation, the equation of the correlation at the scale, the correlation length should be L, and if you enlarge your scale of observation, the system should enlarge the correlation length as well. So this is a very rigorous test. Also, you should see zero magnetization. This is triggered at near critical temperature, and of course above. You should have that the number of domains that are pointing up and the number of domains pointing down should be approximately equal, meaning that the magnetization should be zero. And also, you should see large-scale avalanches, meaning if you perturb one of these metastable states and you provoke a perturbation, this perturbation should propagate after you collect the statistic, following some power law with some exponent, depending on the dimension of your system, etc. The equivalent that if you have a critical temperature and you flip one spin, the possibility is that nothing happens, but also the possibility is that the entire magnet reconfigure. And so you have this avalanche propagated through the entire lattice. At smaller scale, and these are the references of the paper which we prove there, at smaller scale, you should see also neuronal avalanche. Now you focus onto a very small domain in which you can measure the activity of hundreds of thousands or a million neurons. You can probe and put some electrodes. And again, over there, you should see that activity occurs at birth. And these births, according to the correlation that you expect in the critical state, should decay with some exponents, like a power law. The third point, in which we started to work more recently, is that if you see this indication of criticality at behavioral level, meaning what I do with all this stuff going on in my head, should also show the same properties. You can have some dynamic going on in the brain, and then some magic filter that produces some dynamic macroscopic behavior outside. There should be some correlation between the two. After all, psychologists have been doing this all the time for years. They only look at the microscopic phenomena. The microscopic phenomena shows that adaptive behavior, meaning you healthy surviving in that environment, your behavior is bursty and apparently unstable. Okay, I'm using all this word. What means bursty? It means exactly what Manolo is doing. Manolo, you're not doing anything for months, And then one day you work, and then nothing happens for 3 more weeks. And so this is the signature of being healthy. The person that goes to the office from 9 to 5 is a sick person. Actually, adaptive behavior, the way in which we adapt to changes in the amount of food, the amount of money, the amount of salary, the amount of publication, whatever, is exactly this doing nothing for unpredictable amount of time. So this apparently unstable is what really characterizes healthy behavior. And always at the age of failing, observe at what I call the raising the bar effect. When you teach a kid some task or some sport or anything, even if you play a video game, you tune the difficulty to the age of failing. Is almost you are sure that you're gonna frustrate yourself, because if you don't do that, it's too boring, it's too easy. So all your life you keep raising the bar, meaning that you came back to instability. And this is from day one at nursery school to postdoc and whatever. The entire life you're changing you're moving the instability to productivity. So at the behavioral level, we should be able to measure this thing and to be able to distinguish healthy behavior from unhealthy behavior. Okay, I used my first half an hour in all this introductory consideration. Let's show the data. This is the paper I mentioned before with Victor. What we did in this paper, I'm going to summarize very quickly. We identified a brain functional network, meaning it's not a connection, but the brain is functioning, and we measure correlation between 2 points, and if the correlation is larger than a certain value, we put a link. Okay? We don't ask, there is a connection or whatever. We don't know anything about the connection, and even we don't care. We try to monitor the activity, and from the activity we identify links, okay, which is what is thrown here. In this audience I don't have to explain too many about this. And if you count how many links each node has, and you plot in this particular way of the statistic, this is the number of links, and this is the number of times that you count that the node have a certain number of links. You see this is carefully distribution of links. Okay, so at that point, people were asking me, oh, so the brain is like the internet. And I said, no, this is the underlying skeleton of some complex system doing something. The network is just a way to visualize the functional connectivity. Now, it's so true that Daniel Freiman and Pablo Valenzuela in Buenos Aires make an Ising model with only local positive interaction. Meaning, take a system that is extremely well known in physics, put some local connectivity, move the temperature of this model, and when the system was a low temperature, calculate the network of interaction in the same way we did with Victor Aguilusi in 2003, and the degree distribution at low temperature looked like this. There is some favor value, this plot, the same type of plot that we did here. Okay? You see that at low temperature it looked like this, a high temperature looked like this, but at critical temperature it looked like this. And these are 3 different networks with 3 different thresholds. But the point is that only at a critical temperature you have this fat tail distribution of coactive nodes. And remember, these are coactive, they are not connected. The magnet is only connected to the 4 neighbors, which is the little peak over here, by the way. So this is an example that you get this scale-free, long-range functional connections.
I'm sorry, I don't understand how do you get this functional network in the Ising model.
You don't. Do you want me to explain?
Yes, please.
Okay. So before before I explain, because maybe we run into problem of definitions. This paper is published in 2008 in Physical Review. Okay, so you have an Ising model. It can be a Boston model, it can be any of the models that you're familiar with, in which you have some specific implementation, which I will direct you to the paper to see which implementation we use. But let's suppose that you use the standard, much simple way in which you run through some number of steps in your Monte Carlo, and you take an average of the configuration in all these, let's say 10 time steps. But it's okay. And now you take that value as your observable, and you have now a time series for thousands times tens of time steps in your simulation, right? And now you have one of these for each local neighbor, let's say 5 or 10 spins around. You follow me, Maxi?
Not completely. What are you calculating? The average magnetization locally?
You can do that, or you can, that's the pain of the implementation. You can make an average over a certain time, let's say 10 times step, depending on the update of your model, or you can take an average, let's say 5 or 6, you can coarse grain, if you like.
No, in your first option, if you just take the average over the whole system.
No, actually.
Okay, that's what
You're trying to replicate what you do in the brain. What you do in the brain is you take a voucher of 3 by 3 by 3. So you have to do a coarse grain. If I go to 1 neuron at a time, I'm not going to get the same result.
You're calculating an average local magnetization.
Yes, but again, you can ask me, if I ask an average, say, okay, how big is the average? In order to answer precisely your question, you have to look at the precise implementation there. But it's not crucial. The crucial thing is that you put a proof, and you have to define that proof is a local field, it's not a mean field. And you take many of them. Let's say in this case, it's about the same order than in the brain. In this case, it's 40,000 local proof in a system, I don't remember precisely, but imagine that is 10 to the 6. Okay, meaning you make an average of 4 spins. Okay, are you follow me? Okay. So now you have a time series of the local orientation, average local orientation. You're going to call it local magnetization of 1 point, and you have 40,000 of them. You now calculate the correlation of all-to-all correlations. Okay? And you have a matrix of all the coefficients that are coming from this 40,000 time series. Okay? So if you calculate that at the supercritical temperature, of course, all of the matrix will be zeros, because everything will be correlated to the next neighbor very weakly, and then nothing else. If you calculate on the subcritical, you will recover basically the configuration of the lattice.
What is the degree in your x-axis?
The degree is the number of links. It's exactly the same degree, the number of links between nodes. And again, these are the time series in the brain. It's exactly the same what we did in the Ising model. You have the correlation matrix, means are the coefficients, the linear correlation between the 40,000 time series. You take a threshold, everything that is larger than a certain value, you put a link, and then you count the links, and that's the degree. Right?
And the specific is the number of areas that are on at the time step.
What?
You said there's not a snapshot of your time series. You can how many are on at that time, and that's the degree.
Right.
These are all the ones that are connected, that has a correlation which is bigger than a certain
Yeah.
threshold.
Okay, so there are two things to clarify. If you go too precisely, if you go too deep into your definition, not too deep, if you coarse grain too much, you recover speed. Okay, you can analytically know what is the correlation very well. If you if you do the other extreme, if you take the entire lattice, you know what's happening. But the other thing is, of course, if you wait long enough, everybody will have a link to everybody. If you make an infinite simulation, all these blobs will move around eventually, and you will have a different member of your network. But what will remain is that no matter how long you do, you will have that you have domain which has a bulk with neighbors that are strongly connected, and those domains will have this scale-free distribution of size, because you know that the domains are fractal and so on. And so that's the reason, as if you entertain yourself and read the paper we discussed it there, that's the reason that only at the critical state, although the connectivity is a lattice, imagine other situations. You can have a network if you like, you can put a network here. But the correlations will be dominated, the degree, the functional degree as we call it, the functional degree will be dominated by the statistic of this domain. And these domains have a shape that it doesn't care if you're simulating an ice, if you're using a water, whatever. That correlations are coming from that. And that's what we discussed, that only at the critical temperature, the icing, and that's why the paper is called icing-like dynamics, in that scale. And this is independent if you talk about the brain, if you talk about any other system. You will have a functional network which have this fat tail, and these fat tails are coming from the dynamics and criticality. Is that clear? Again, this is, I repeat what I said at the beginning, the network, the brain is not like the internet, I don't care. The network at that moment was a way to be able to measure something that is only appear at criticality.
Isn't it ironic that you want to make the contrast between that this is rather collective behavior and not based on connectivity?
Ironic? That's a fundamental point.
Yeah, but then you choose as the name functional connectivity, while it's neither connectivity nor functional.
Yeah, but if you read this paper in page 73, it says,
We don't want to read it, we want you to explain it to us.
I know. That's what I'm trying to do. I'm new in this business. That's what I'm trying to learn. Again, in this paper, the chapter that I described, that is called functional collectivity. And functional collectivity is the name that is given by more than 50 years. But the paper, the title of the subsection is called functional collectivity. These are other things that Victor, in the newspaper in 2003, we look at the assortativity of this network, and we found that the degree of was positively correlated with the degree of the first neighbor. And at that time, we were not able to understand where we're coming from. This is the brain, and this is the icing model. Also, the particular way in which the degree goes with the degree, the average degree that was flat instead to go down, and the icing goes like that, and the brain goes like that, very similar. And the clustering coefficient also, as a function of degree, is very, very similar to what happened in the icing model. So we were convinced that indeed when we were looking at the brain, we were looking at the critical temperature, the icing was very, very similar. Okay, I need to speed up, so with your forgiveness, I will just look at zero magnetization. Zero magnetization, what we do is we cannot count how many spins we have had, how many spins we've done. We cannot do it for the entire brain, but what we can do is to choose a place, let's say this region. By the way, this shape over here is one hemisphere of your brain, flatten it, okay? And in this case, this is the frontal cortex region, and whatever is being colored yellow or red, it means that it's lined up with this point. So I choose this, I call it a seed, and calculate the entire correlation with the entire brain, and whatever is correlated with me, I'm going to paint it hot colors, and whatever is against is in anti-correlated when I paint the blue. So I guess that this in Max's language will be one opinion and another opinion in some opinion model. And if you calculate that, and you make the ratio of these two, this ratio for normal individuals is about 1. This is the medial prefrontal cortex. The ratio is about 1, is the number of places, the number of square centimeters of the cortex which are found that the brain is correlated divided by the brain anti-correlated. Okay? Of course, choosing some threshold. And if I do it for another region in the parietal cortex, the ratio against is 1. And so, in all these 6 places, which are classical places to look for these things, the ratio between one and the other is about 1. This is exactly what we call zero magnetization. Number of pin going up and the number of pin down ought to be approximately the same. This is what is shown in this column, in which again the colors are the opposite for the 6 different conditions. These are about 6 different brains, these 6 different individuals, and these are patients that have chronic back pain. Patients that have chronic back pain have suffered chronic back pain for a number of years, and we described several years ago that indeed this affectation changed the way in which the brain is working for a number of reasons. People that have chronic back pain have no cure. It can take 5% of the population that have chronic back pain evolve to chronicity. Another 5% commit suicide because it cannot do anything with their life. It's a very serious condition. And if you calculate the same thing, you see that yellow is larger than the blue, and when you calculate your ratios are 30 times different from the normal condition. So this is 2 for the price of 1. You have the quantification of the zero magnetization condition and normal condition in a healthy subject, and when you take a mental state that is affected by a condition that affects very seriously the individual, you have that ratio goes out of whack.
So are those data from functional N and L?
Again, see, this is the paper in the Journal Science 2008. This is the same kind of data. I'm talking always the same functional MRI. You have time series on 40,000 different places, and you do all these processes, and then you start counting beams like any other case. Now let's get something even more. The divergence of correlation length means, and if you take a magnet of 1 centimeter and you take a magnet of 10 centimeters, of course the magnetization will go to the 10 centimeter, which means there's going to be a domain of equally aligned spins of 10 centimeters. And now, if you are smart enough, you take an iron of 100 centimeters, and you have that indeed the magnetization goes to 100 centimeters. Okay, so that means that the degree of correlation diverges with size. No. What really diverges with size is if you take that iron and you bring it to the critical temperature, okay? And at the critical temperature, you measure magnetization, and now you take the fluctuation around the mean magnetization. So, it's the fluctuations around the mean. And the fluctuations around the mean means that the domains of equally aligned spins, the fluctuation of these domains. And now you calculate the correlation. And when you calculate the correlation, you will see that this correlation eventually reaches 0 and eventually goes to negative because you have the anti-correlated domains. So you measure that length at which reaches 0, and that's the correlation length. And if you measure that in your magnet of 1 centimeter, measure that in your magnet of 10 centimeters, measure magnet of 100 centimeters, you will see that that correlation length diverges with the size. And that only happened at criticality. So criticality, this divergence of correlation length is a very smart way to look for see if you're near criticality or not. So it turned out that Giorgio Parisi measured correlation length for this system, for a population of birds flying near the terminal grove. And of course, this is the pattern that evolved in time, and you will take the average velocity of all the flow, and you will take now the fluctuations around the average, and that will be your signal to calculate correlation length. And you will calculate correlation length of this flow of different sizes, and that's what Parisi did. We're going to do the same with the brain. What are my flows? My flows are these things painted yellow and red. And what is this? These are the areas that are active above the average, which is how I did this picture. So this is a real brain, again, it's a subject, lying doing nothing in the scanner, and I'm going to try to convince you that the correlation, the divergence of correlation and here are the same. So this is what Parisi, actually Cavagna et al. in Parisi's lab did. You take all these birds flying, you take these are the full velocities, you take the average velocity, you subtract it, and you get all these birds speeding up, all these birds slowing down. And again, these birds have local connectivity, they're only looking at their neighbors. That's a discussion we can have later. And you calculate the correlation length, goes from 1 to 0, and then goes to negative. This means you have calculated this for every pair of birds in the flock. You take 2 birds, you calculate over time the fluctuations around the mean, you calculate linear correlation, and then you say, if they are very close, you put your point here. If these birds are far apart, you put your point here, and so on. And you take the average, that's the correlation there. Now, see what happened. This is a flock of 10 meters. Let's say one day in the termini, they film 10 meter flock. Next day, the flock has 30 meters average diameter. More birds. And so, and you put all your data, and you see that the correlation length diverges as the flock size. That means that a flock of 20 meter diameter, 2 birds that are far apart, about 6 or 7 meters, that still correlate. Of course, it's the only way to remain together with the flock. If they decorrelate, they form 2 flocks, and these 2 flocks are smaller and so on. So it is trivial. It's trivial that in order to fly together, this is the correlation length and the flock size plot that you have to have. But it's not trivial how they do that. The only mechanism that we can write in which you will have that the correlation length diverges like that is that the flocks, dynamically speaking, are critical. So these are examples, and let's do exactly the same for the brain. So this is my data. Each image is taken every 2.5 seconds. In each image, I will have regions that are above average and regions that are below average. Whatever is above average, I will identify as collections of boxes which are whose fluctuations are correlated. Okay? So I'm going to identify my flocks. It doesn't matter how I do it. I do it with the clustering algorithm. And if you cluster the algorithm, you'll have these flocks that are identified, which are similar to the flocks that you see before, dynamically speaking. And now you calculate the same thing, correlation as a function of distance. If anybody does not understand what I'm saying, please ask. I have identified flocks in a way that you don't need to understand, which are regions of the brain that are coactive, about an average. These flocks, I have the coordinates, x, y, and z in the brain, and I have the time series. I use this time series to cross-correlate with everybody else, and then I plot it as a function of distance, okay, between the places in the brain. And each of these curves is one of them, meaning I have about 30 or 40 different flocks, each one has a particular correlation. And I take the zero crossing and I plot over here. And you see that it's exactly the same plot in Palisica for the birds. Correlation length, increase with flock size. And now, if you take all these correlations, functions, and you normalize by the correlation length, this is what you get. It's not a perfect overlapping, but it means that there is only one correlation function for the entire system. But in neuroscience, people don't talk about correlation. In neuroscience, people talk about information. So I don't know how Professor Plastino feels about, but I feel that information in the brain is just another name for the same thing that I'm doing for correlation. But you can calculate correlation, the mutual information, okay, as a function of distance. So with the same time series we did it before, instead to calculate correlation, you calculate mutual information, and you set a threshold, okay, let's say 0.4, and now you define your correlation, your mutual information length, meaning how far apart two regions of the brain do not know about each other in information terms. And when you plot it as a function of the size of the regions that are interacting, again, you have this divergence of mutual information. And when you rescale mutual information by the divergence, correlate mutual information length, you get a nice overlapping of this function. And this paper was sent to PNAS 2 years ago and still is under review. Then the same paper sent it to PNAS 2 years ago. We said that means that indeed noise in the brain. Again, back to the slide number 1. What means noise in the brain when people talk about these fluctuations that were added to the model or whatever in order to get this switch? So let's just calculate the variance for a blob, meaning for a flock of birds in my head, for the same data that I showed a minute ago, that have 39 components, 39 boxes. So a relatively small region of the brain that is acting together. Let's measure the variance, and for a region of 39, a region of 54, 800, 6,000. And let's plot, this is the time series, and this is the variance, and this is the size where it's coming from. You see that this is plotted in the same axis, in the same scale. You see that the fluctuation of something small is of the same order, the fluctuation that is 4 orders of magnitude larger. Such that when you plot size, variance versus size, is constant. Now, when I show this to my colleague in neuroscience, I would say for the camera, they are not able to appreciate how deep is this. Because it is usually neuroscience to average things to get better signal. We take many places in the brain, average around, let's take 20 more in order to get a better signal. Because under the conception that indeed more degrees of freedom, the variance will decrease, like in the case in which you have here, like the standard 1/n. But indeed in the brain, you average and it doesn't go down because the character of this fluctuation is anomalous, which is exactly what you get in criticality. If you average, again answering the question that Maxi put at the beginning, we realized that when we were trying to define a local temperature for the icing model, it doesn't matter if you take 5 around, or 10 around, or 20 around, because what you get is exactly, it's not exactly the same, but statistically speaking, it's anomalous fluctuation. So this is real data, and indeed, although the title of the paper is Optimal Information Sharing in Brain Resting State Network, one of the messages is that indeed fluctuations are anomalous in the brain, and it doesn't matter how big is the size that you average. This is a typical fundamental property fluctuation. I guess that I will have to wrap up. There are many more material I would like to cover. I will not be able to show you more than a couple of more slides. But this was posted 2 days ago, and I think that in physics it's typical to show you last week result. This is something that I'm very excited because if I'm right, and all these fluctuations are coming from criticality, there is much more that you can dig. See what we did here. This is the time series of one region in the brain. In one box. And things that goes up means that there are more activity in that region. Now, if you truly believe that indeed these transitions are like in the domains in the Ising model, you don't want to have the entire time series. You don't want to keep track of the entire evolution, because what matters is the transition. Once the domain went from up to down, why you have to keep recording that is up? Indeed, if you believe in what you're saying, you should only keep your point, which is what I did here. I put the threshold, and I took a point. And I convert the time series, which is the real values through time, in a point process. So out of these 600 points, I end up only with 20 points. And I throw away everything else.
Which points you get?
The crossings. So you normalize it, take a 2 standard deviation, whatever. 1 standard deviation, say, I take it, like a Poincaré section. And the idea is, if you really have a flow, the Poincaré section contains most of the information. And so in the Poincaré section, you can keep the coordinates of the intersection, or you can keep the times. In this case, you keep the time. Okay, and what do you do with that? See what we do. These are the standard results with independent component analysis, which everybody knows what it is, of the entire brain data, the 300 gigabytes of data. Okay? And these on this column, which you should compare visually, are the rate of occurrence of one point with everybody else. Meaning, I have this point, to calculate these maps, I have only used the points in space and time when there is a transition. It's a file that you can manage with Excel. It's about 30 points over 600 points in each time series, times 40,000, so you end up with 1,500 points. Now, what you do is you calculate, if I have an event, a transition, where is a transition in this time step and the next time step. Let's suppose that in opinion model you say, somebody has changed opinion. Where in the lattice, in now or in the next time step, there is a change of opinion. And you put a dot there, and you compile this statistic, and then you put some color to say how this, call it functional correlation happens. And this is what you get, extremely similar. And if you calculate how good you do with 3 points, this is what you got. You should compare this with this. Okay? 6 points or 12 points. So meaning that you have 3 events, and with 3 events, you run around the question, if I change opinion here, who else is changing opinion? I mean, if there is a transition, where else is there is a transition now on the next time step? And you get a pretty good result. And if you calculate some correlation as a function of number of points, you get some asymptotic, about 10 points. So this is a very strong result, which not only is good from the theoretical point of view because it matches what we're doing, but let's do something more. Now I have 1,500 points. I can ask a lot of questions because it's extremely easy to run an analysis. Let's ask how much of your brain is active. For instance, Ernesto right now is asleep. Okay? So, in Ernesto's head, how many clusters were a few minutes ago switching? I have to again make use of a clustering algorithm, but I do clustering points of very small files. You do it by hand. And I paint green or blue or red or whatever. I have about 6 clusters. And then in the next step I have 1, 2, 3, 4, 5, 6, 7, 8, 9 clusters, and so on. In each time step, you count how many clusters you have. It's like asking how many clouds I have in the sky of Mallorca. You count 5. And now you count. And how much stuff is there, meaning the integral of all the clouds. How much density of clouds you have. Okay? Why is that important? Because after all, the business of the brain is using independent clusters to execute some behavior, and you have to use all these resources if you want to. Otherwise, why are you going to have a piece of the brain that never slide up? So the question is relevant to understand how big is the repertoire of dynamical state. Okay, here is the number of clouds over time, like the number of clouds that I identify, but in this case I did it with dots. It's extremely easy to do it. And this is the maximum size, the size of the largest component, meaning you count how many clouds are in the sky now, and what is the size of the biggest cloud now. Half an hour later, you do the same. You say, you have this time series and this time series, and see what happens. When you plot everybody against everybody, you have a plot in which this is the number of clouds, and this is the number of active size, means the density. You see that initially it rises up, and then falls down. Take a minute. This is Ernesto sleeping before. One little cloud, very small. And this is one big cloud covering the entire brain. Now, everybody familiar with percolation, you go up, and you are in the middle here, in which you have many clusters which start bunching together. So this transition is well known for you guys. But it's the first time that we were able to measure in the brain, because in order to do this with the entire time series is impossible. Now, see what else you can identify in this data. Well, if you go to the time series, you will see that when the maximum size, when the cluster is very big, you get this anti-correlation. Yeah? The cluster number goes down when this guy goes up. And there is this line, about 2,500 voxels, which correspond to this line over here. Means that we know now that in your brain, on anybody's brain that we make it put in the scanner, there's going to be a transition around 10 to the 3 voxels that are active. A transition in which things will start bunching up. So let's ask the other question. What happened in this size? How many clouds you have in your head at the transition? Meaning, there's not millions of possibilities of clouds in Mallorca. Either you have the entire Mallorca covered, or you have only few clouds. Because when clouds start bunching up, you have the transition to the entire sky. It's a dynamical transition. So see how many you have, 10 to the 2. So this is the number that I mentioned before that was important for us. How many clusters, independent clusters, meaning how many regions of the brain are independently being excited in the brain? 10 million, 10,000, 10, it's about 10 to the 2. And so this is the number that we were going after before. Why this number is 10 to the 2? Now, since Brodmann, in 100 years ago, we know that there is about 100 regions in the brain. There is not 3 million or 3,000 or 20. There are about 100. So the question is this related trivially to Brodmann? Is this trivially related to the fact that indeed the number of areas that the repertoire we have, etc. I will finish with this because I guess my line. So let's keep track of these clusters. Again, now we can do that because it's extremely easy to keep track of points. And if you define an avalanche as something that have either a neighbor coactive up to the moment in which there is nothing followed to this, essentially the same way that you define earthquakes, and you compile the size of these avalanches, and you pile up in double log. These are 6 individual subjects, 6 different individuals scanner, you have a nice 3/2 exponent in the distribution of this avalanche, meaning that during the activity, the normal activity, during these flocks flying in your head, etc., indeed what you have is a spread of scale-free avalanches of activity in this cluster with all these properties. And the lifetime distribution, meaning the number of steps in which you can see fall off as quickly, and this is another important thing, is it's about 10 to the 1 times 2 is about 30 seconds, the longest avalanche, length of avalanche that we measured during these experiments. There is other exponent like the fractal dimension of this avalanche, which is about 2.1, which coincidentally is the same exponent as for clouds. And I guess that was only the second point of my talk. I will keep next time telling the story of small size. I guess that I covered only these I will say these 3 steps. Functional correlations are scale-free, are comparable to those things near TC, the Ising model. I guess that I pretty much convince you of that. Zero magnetization is only seen here in the brain. It's a strong indication that there is a balance between all these regions in the brain. I guess that also you are convinced that correlation length diverges with size, pretty much similar to the other collective systems like the case of Parisi experiments and Gavagna. I guess that I finished with this jamming and scale-free avalanches of large size, and I'm only being able to visualize this technique of point processes, and some other time I will talk to you about these points. Thank you very much for your attention.
Thank you very much. Thanks, Doctor, for questions or comments.
No, just I probably misunderstood it. When you explain with the models some part of the functional brain behavior, you use a structural model because you use the easy model with nearest neighbor, you use the burst model with nearest neighbor. Would you be tempted to say that the brain, long-range connections in the brain are not relevant for the dynamics?
A different question. So, as you know, there are places in which, and there are questions that are answered by models in which all the coefficients are there, and you solve the coefficient at equilibrium, and that's it. And you get what you want. Okay? And that's what's in physics. If you see the success, the main success of theoretical physics is in models in which precisely everything is there. You have the equations, you have the coefficients, and nothing changed. There is no resource of there is no hidden layer doing the rest. And that's the problem with the brain. The brain is not one of these models. The brain is not. The brain model is one of these models. And that's the reason why it took so long for people to even start paying attention to how you address this. For me, it's obvious that there are in the brain phenomena, result, observation, very regular, I would say it's fundamental, if you like, which are pretty well modeled by that kind of model, in which everything is in the coefficient and the equation of motion of each element. But there are plenty of phenomenology that is under the rug, which belong to the problems that I described, that are fundamental to understand the brain, which are not obviously modeled by that kind of approach. And that's the reason why people don't want to get involved, because it's extremely difficult. What is the difference between what I do and the rest? Every claim, there is an experiment. The observation is very clear. The system seems to be near criticality. If you don't address that, you will not get the answer that you have. That's my claim. And each claim there is an experiment behind. So what you're asking me is, how much of what you see there can be explained with long-range connection?
No, I mean, is it important for you? What do you think? Do you think that long-range connection in the brain is important or not? That's a feeling for me. not saying anything.
Well, it's an opinion. Anything for the camera. Who's going to get offended? There are a number of papers that claim that they can match. Let's see the experiment. Let's see the data. Let's not talk about it. Honey, Honay, guy student of Olaf Sport. He measured diffusion tensor imaging, which gives you the structure. He measured functional MRI, which gives you the dynamics. And then try to match what is being explained by the structure and what are the functions being explained by the structure and what is not. And there's a number of things which were not explained by the structure, but it's not the main focus of the paper. So, depending on where you want to put the half empty glass. I think political.
So first question, first answer.
Referring to the two books you mentioned at the beginning, what I understood is the following. Those two books are dualistic in some way, Cartesian dualistic, because they put some external agency that controls the price. And maybe you have discovered the answer to dualism, that is in criticality. That is what I understood.
Thank you. There is no other, if anybody in the audience knows how to solve the problem that you have, obviously a dynamic which it is extremely diverse, is changing all the time, and somebody claimed that this goes through the network. If anybody knows a way to solve this conundrum of having another brain controlling this brain, let me know. What I say is that I don't solve the problem. Of course, I did not solve any problem, but I said the only way to have the flexibility of having a structure that I show in the easy model, which have a different dynamics, is a criticality. It's too obvious. If it's too ordered, it's like the same I used to the image of the water goes to the rivers. Of course, you know where the rivers are, you know where the water is. Okay. But the brain is a different river every time. So either you have somebody that is controlling where the water is, or you will have to have a big avalanche of water all the time. But I have to recognize I'm not solving the problem. Because you can ask me, Dante, who is doing the changes, the dynamic? So you say that the brain is doing whatever he wants? I'm not solving the problem. I'm saying it must be in that direction that we have not considered. You say, if you came here and have avalanches, I remember the first question I got many years ago, like 15 years ago. Michael Schlesinger, a very smart person, in a conference in Colorado, said, Dante, why is it good to have avalanches in your head? And I said, Michael, you have one. But the interpretation we make in avalanche is something that is noxious, that is something bad, that is something that behavior is something that we are computing something and this and that. Probably it's not as complicated as that. And remember, my friend was Pervat. Pervat will say the brain functioning is an interpretation that you make from outside. And we get too philosophical. But I will stop here. I guess.
The last question.
My question would be, the way you put is that the most interesting behavior is when there is or a large degree of sites working of the order of 100. But if you think of many of the experiments that are done in psychology, you are asked the subject to do something very specific, so you open your eyes when you see that thing, so you activate a very few regions of the brain, probably, one for whatever. So, would your results imply that the way you should address that is not by looking at what is happening when you do very few simple tasks, rather than looking at a more complex behavior where many things going on simultaneously and so on?
Precisely, because look at the variance at the critical point. The variance here is the largest variance, which is another indication of criticality. So if you instead to subject the subject, to put the subject in a constraint, in a low temperature regime, and say, tell me what is 2 plus 2, which you know the answer. Right? Instead to do that, you try to see what the system is able to do, you will discover this kind of things. So for instance, yesterday I was working with Pedro Montoya and say, Pedro, let's just think crazy. And so I told Pedro about this, which I believe this is the most susceptible point of the brain. This is the moment in which you put one more cloud and you get the entire sky covered. So you know that the point of maximum susceptibility is the critical point. In physics, that's precisely the definition. If a single perturbation will produce either nothing or everything. So it means that if we can design an experiment to in real time measure the number of clouds you have in your head and see if when we perturb there, you get a different quality of response. Right? Why is important? We're interested in humor. Actually, with some of the students of Pedro at the postdoc, we are running an experiment with humor, what make people laugh. Okay? And we are measuring while they look at the movie, what do you use for the movie? The Simpsons. People are instrumented with EEG. Okay? So we believe that we can measure EEG at the same time in several individuals and show that indeed when they share the Simpson, they will synchronize, or measure actual synchronization between EEG of individuals in a way that it will be optimum if they are close to the joke. And we will have people that bring lousy sense of humor that will never synchronize. So if we then take these individuals and we measure how is the distribution of these things, we can start making links. Another example is depression. Depression is a dynamic state. There is not a neuron 43 that is wrong. Bipolar syndromes. Most of the mental state or the mental diseases are dynamic state. So the idea is to not to run another experiment to see what area of the brain lights up when you calculate the square root of 2, but to see if we can objectively measure your mental state, if we can perturb it, if we can improve your humor, if we can make you laugh independently of your sense of humor, if we can manipulate the state of mind. And this is fundamentally different from controlling you to shit a light and blah, blah, blah. It's a different kind of question. I'm not saying that the other questions are stupid questions. I'm saying it's a different class, and technology allows us to do this kind of thing.
Okay, we can continue discussion outside.
Cuando defines las áreas, esto depende de donde origen, supongo, el nivel de programación. O sea, cuando tú supongo que hay un margen y nos vamos a nuestra algo parecido.
El tamaño del componente más grande, el giant component, como función del nivel de compresión. No sabéis que el tamaño del componente gigante hace un pico al threshold de compression. Entonces, él fija el threshold. Si haces eso,
o sea, O sea, o haces en función de los parámetros que obtienes. O sea, digamos, los resultados fijas dónde están.
Cuando trabajamos con Víctor, mostramos que era robusto para cierta variación de parámetros. Ahora ya no lo tenemos que hacer porque Dimitri lo que mostró es que si vos en lugar de explorar paramétricamente elegís la correlación a la cual tenés el componente más grande, ya te sacas el probabilidad.
Entonces utilizas eso con la correlación y ahí es lo que te da, por aquí está conectado, por aquí abajo no está. Oye, hay café y pastas ahí, sí. Te lo digo porque...
Vamos.
Só uma pergunta, o modelo de Ising tem os spins, o modelo de Ising. Ising model you have the up and down spins. So what would be the minimal dynamical unit in the plane? You have like arbitrary voxels and the fMRI data, but then you can have beds and planes.
It's a matter of coarse graining. So, el coarse graining lo definimos. Nosotros, en este caso, por razones biológicas, tenés que el máximo de solución es de 2 milímetros por 2 milímetros por 2 milímetros de cerebro.